Good morning, students. Today we are going to discuss about the Kirchhoff laws. In the previous classes, we have discussed about the Ohm's law and also the combination of resistors, combination of the cells. So those laws can be used for analyzing a given circuit or a network. What is the meaning of network? If many components, many different components are connected in different ways, series, combination, parallel combination, and like that, in a complex manner, then that will be known as a network. So here, there are different ways to analyze a given network. What is the meaning of analyzing a network? You have to understand that first. Analyzing means it is to find out the value of the current which will be flowing through each of the component. How much current will be flowing through each of the component. So determining the value of the current and also sometimes potential difference, sometimes the resistance. So that will be known as the analyzing a network. There are different laws available or developed for analyzing the networks. The simplest one is Ohm's law, which we have already discussed. Then the next step is to study the Kirchhoff's laws. Even there are more laws which are not included in our syllabus. Therefore, we are restricting ourselves to the Kirchhoff's law. There are two different laws in which are proposed by the Kirchhoff. We are going to discuss each of them with examples. And I think when we discuss the example, then meaning of the Kirchhoff's law, so that will be clear. So therefore, let us start discussing about the first law proposed by the Kirchhoff. So here, the first law which is proposed by the Kirchhoff is known as Kirchhoff's junction rule, or it is also known as Kirchhoff's node rule, or it might also be known as Kirchhoff's current law. These three are one and the same. They are not three different laws. It is the same law having three different names. So first, we need to understand what is the meaning of the junction or node. Junction and node are one and the same. What is the meaning of it? You might have heard the name of the junction. So it is the point where more than three paths are connected. That is known as a junction. If there is a path which is going like this from place A to the place B, then it is known as a road. If at some point there is another path is meeting the given path like this point is known as, which goes to the point C. If you start from A, then either we can go to the B or we have a choice to reach the C. So this point where the two different paths will meet, that is known as a junction. Similarly, if there will be more number of paths meeting at the same point. So that will be known as a junction or the node. That is the general meaning of node or the junction. So here also, we are not talking about the roads, but we are talking about the components. Components means it could be resistor, capacitor, cell, or even inductor or transistor, anything. It could be anything. But in our discussion, we are restricting ourselves to only two components. One is the cell, other one is the resistor. Only these two components are considered throughout this chapter. So therefore, when we consider a network, complex network, in this chapter we can find only these two components. There may be number of cells connected. There may be number of resistors connected in different ways. Now, let us consider the meaning of the junction or the node. So this is applicable for the junctions. So that's why the name junction rule or the node. Now let us consider the different components connected at a given point, which is known as a junction. Like this. So there are 5 different points. From this junction, there are 5 different paths available. So because of these different paths, the current will be flowing. It may be a part of a large network. So we are going to consider a single point where more than 3 or more than 3 components are interconnected. That point is known as a junction. And many currents, and these are different branches. And in each branch, different current will be flowing. And I am going to represent those currents as I1, I2, I3, I4, and I5. Even it could be many more. Simplest one is 3, but I have considered 5 different branches here, which are connected at a single junction. And we know that here the current can flow in 2 different directions. It is not a vector, but it can flow in the wire itself. It cannot leave the wire. It should be flowing in the wire itself. It cannot flow like this. That means there is 2 possibilities that current can flow in this wire. One is, since we are taking the junction as a reference here, reference point, the one of the direction is either it may be towards the junction, like this, represented by the arrow, which is directed towards the junction, or another example, I will take it as away from the junction, so which is represented like this. That means here I1 is flowing towards the junction and I2 is moving away from the junction. Similarly, we can give any direction to these currents. I will represent it as I3 is moving towards the junction, I4 is again moving towards the junction, but I5 it will be moving away from the junction. This is how I have represented the direction for the different currents. It could be anything, but I have chosen this path. Now you can see that among these 5 different currents, I1 to I5, 3 of them, I1, I3 and I4, they are flowing towards the junction. So I1, I3 and I4, they are flowing into the junction. Whereas other, which is I2 and I5, they are moving away from the junction. I2 and I5 are moving away from the junctions. The Kirchhoff's current law or Kirchhoff's node rule or the junction rule, what does it propose? It suggests that the algebraic sum of all the currents at a junction should be equal to 0. That means we have to apply the sign convention. If we assume that it is only our convention, it is not necessary that the current which is flowing into the junction should be treated as a positive. It is not like that. But if we assume that the currents which are flowing into the junctions are taken as positive, then those which are flowing away from the junction should be treated as negative. Do you understand that? It can happen in the opposite way also. But usually what we consider, what comes in, it will be taken as positive. What goes out, so that will be taken as a negative. So that's why the current which is entering the junction, which is directed towards the junction, so that will be treated as positive. And those which are moving out of the junction, That will be treated as negative. So if you put the sign convention here, you can write I1 plus I3 plus I4, but I2 is moving up, so therefore it is treated as negative, and I5 again it is moving out of, flowing away from the junction, therefore it will be treated as negative. So which should be equal to 0. So that's what Kirchhoff's current law or Kirchhoff's junction rule says. This can be represented in a simple mathematical way. If you put the mathematical symbol for the summation, which is suggesting that this is the algebraic sum, not adding all the current. It is adding all the currents considering their direction also, whether it is moving into the junction or moving out of the junction, into in general the current. That should be always equal to 0. This is the mathematical form of junction. What does it suggest? It suggests that the algebraic sum of all the current at a given junction should be equal to 0. That's the meaning of the junction. Is that clear? If you take algebraic sum of all the current at a junction, it should be equal to 0. Now we are going to analyze this equation. Why is this so? Now we know that the current is nothing but the flow of the charges. Here, if you assume that in a particular time interval of say t is equal to 1 second only, unit time, if q1 amount of charges are reaching the junction, say I will represent the junction as P. If they are capable of reaching this point P via this path, which constitutes the current I. Similarly, at the same time, in the same time interval, Q2 amount of charges will move out of the same point. Q3 amount of charges, again in 1 second, they will again reach the point P. Q4 amount of charges in a different path, they will reach the point. Q5 amount of charges, they will move out of the same point, time interval of 1 second. That means the total charges which are reaching the point P, which is the junction, in a time span of 1 second. So that will be is equal to how much? It will be represented as Q1 plus Q3 plus Q4. The how much charge is moving out of the junction, so that will be represented as Q2 plus Q5. The first sum will be representing the total charge entering the junction in 1 second. Similarly, the second sum will be representing the total charge leaving the junction in again 1 second. At the same time, what should be the relation between these? That's the question here. What should be the relation? Whether they are equal or not equal. If they are not equal, then there are two possibilities. Let us assume that they are not equal. Then there are two possibilities. Either the charges entering the junctions are greater than the charges leaving the junction. Then what happens? That means, imagine that this sum will be equal to a quantity represented as 5 coulomb. Other one is will be equal to 4 coulomb. That means the amount of charges that enter the junction is 5 coulomb, that leaves the junction is 4 coulomb. That means in a time interval of 1 second, the difference between these 5 coulombs enter the junction, only 4 coulomb out of them will leave the junction. That means 1 coulomb of charge, it is destroyed. 1 coulomb of charge is destroyed. Okay, remember here there is a destruction destruction of the charges. Similarly, on the other hand, if you assume that amount of charges which are leaving the junction is greater than those which are entering the junction, that means we can say that 4 columns of charges enter the junction, 5 columns of charges leave the junction. What does it mean? Here, in a time interval of 1 second, again there will be 1 column of charges are created. They came out of nowhere and they will be leaving the junction. So it will be indicating that there is a creation of charges. What is the problem with this? Do you have any clue? Why? These two, the charges entering the junction, not equal to the charge leaving the junction. Two of them, either one of them is greater or other one is smaller. Is that possible? Do you have any clue? It cannot be possible. It is impossible. Reason? We have learned it in the first topic itself of the syllabus. First chapter, first lesson. While discussing the property of the charge. Charge is a conserved quantity. There is only redistribution of the charges. Creation and destruction of the charge is impossible. It is a conserved quantity. So therefore, both the cases, creation and destruction of the charges is impossible. That means, amount of charges which are leaving the junction should be equal to amount of charges which are entering the junction. There is no accumulation of the charges here because charges can flow here. They have a paths available for the flow. So therefore, they will not accumulate. They will not get stored here. They will always keep on flowing. Whatever may be the amount of charges which are entering the junction, it should be leaving the junction. So therefore, from the principle of conservation of charges, we know that amount of charges entering the junction per unit time. If I divide it by time, then what happens? Q1 by T, Q3 by T, Q4 by T, which is nothing but I1 plus I3 plus I4. That is equal to, I have shifted the I2 and I3, I5 on the other side. So therefore, it will be equal to Q2 by T, Q5 by T, which is nothing but I2 by I2 plus I5. So therefore, total current entering the junction should be equal to the total current leaving the junction. That's what Kirchhoff's current law or junction rule says. The amount of current entering the junction should be equal to the amount of current leaving the junction. You have to remember that. The significance of the Kirchhoff's current rule or current law is based on the principle of conservation of charges. The question might be asked in the examination. What is the significance of Kirchhoff's current law? That is conservation of charges. That is the meaning of the current rule. Current rule has been developed on that principle, conservation of charges. Definition might be asked. If definition is asked, then we have to write this one. Only this much. That means in words, not in a mathematical formula. In words, the algebraic sum of. It may be stated in different ways. I will quote every possible statement. The first statement is algebraic sum of current at a given junction is equal to 0. Algebraic sum of currents at a given junction is equal to 0. Otherwise, like this. At a junction, the total current entering the junction should be equal to the total current leaving the junction. Current entering the junction should be equal to the current leaving the junction. Or algebraic sum of current at junction should be equal to 0. And what is the principle behind the or significance of the current rule? That is conservation of charges. I hope you have understood this. And there is one more thing that we can find in current rule. Since there should be both current entering the junction and leaving the junction. Therefore, remember that when we assign direction to the current, that we are doing that. It is not given in networks. The directions of the currents are not given in the networks. When we are analyzing the networks, the direction of current is never given. We have to assign the direction. But we have to remember we can do anything. We can put it in particular direction or in opposite direction. Either we can choose I1 entering the junction or leaving the junction. It is our choice. But what happens is, we have to remember that not every current can enter the junction. If a junction is given like this, I will give them 4 currents here: I1, I2, I3, and I4. If I choose randomly the direction of the current, I4 entering the junction, I1 entering the junction, I2 entering the junction, I3 also entering the junction. It is a wrong assumption. Why? All the currents are entering the junction. So then, where would the charges go? Is it possible that all the charges entering the junction get destroyed? No, it is not possible. So therefore, we have to keep that in our mind that at least one of the currents should be leaving the junction. At least one of the currents should be oppositely directed. On the 3 leaving the junction, at least one of them should be directed towards the junction. So therefore, that is what we have to remember while assigning the direction to the currents at any node when we are analyzing the circuit. It will be clear with an example. After stating the other law also, second law also, so we are going to do that. And students, also remember that since the current law is stated first, it is also known as Kirchhoff's first law. Okay, Kirchhoff's junction rule, Kirchhoff's node rule, Kirchhoff's current law, or Kirchhoff's first law. They are one and the same. It just shows that algebraic sum of current at any junction is equal to 0. Or the sum of current entering the junction should be equal to the sum of current leaving the junction. So that's the meaning of the Kirchhoff's current rule. We are now moving on to the next one, which is known as Kirchhoff's voltage rule. It is either known as Kirchhoff's loop rule, Kirchhoff's mesh rule. Loop and mesh are one and the same. Then, since it is related to the voltages, therefore it is known as Kirchhoff's voltage law. It is stated after stating the first law, so therefore it is also known as Kirchhoff's second law. They are one and the same. But what is the meaning of this? What is the meaning of loop or the mesh? We know the meaning of the loop. It is a closed path available for the flow of the current. It may be a part of the network or entire network itself. A loop or the mesh is a part of the large network or entire network itself, which gives a path, closed path available for the flow of the current. Okay, so therefore that is known as loop or the mesh. I will draw a simple loop. I will draw a network. So there will be some network like this. It is a network, somewhat like this. There are resistor cells like connected like this. There will be different resistors here. In every branch, there will be resistor cells connected in a complex manner. If I take this point, this is a junction where more than three components, three or more than three components are interconnected. And remember that every junction in a network is represented by the dark points. We should make it dark dots. We have to place a dark dot. If we start from this point, there is another junction here. There is another junction here. There is another junction. So if we start from this point, say A, then B, then C, then D, then again back to B. From starting from this point, then if we are able to reach the same point, passing through different components, so then this is known as the loop or the mesh. It is one of the mesh in this large network. Similarly, we can find another loop, which is somewhere here. This is another mesh. Are you able to see that? Let me try to change the color here. So another mesh like this. One more mesh like this. Now carefully observe. I will take one more mesh. Starting from the A itself. But somewhere here, then here, then here, then here, then back to here. This is also a mesh. Which involves the two meshes we have already considered. So it is a closed path available for the flow of the current. That will involve the IR drops, the voltage drops, which is governed by the Ohm's law. And also, it might include the cells, EMS. Both are included. That's the meaning of the mesh. Now, once we have made the meaning of loop or the mesh here, now we can move on to the voltage or the mesh. What is the meaning of this? Now I am going to consider a simple mesh or simple circuit. Not a complex network, a very simple circuit, right? Given in the diagram. So here, there is a cell. Then there will be a resistance. Then there will be again a resistance. Then again there will be another cell here. Okay. Then they are interconnected. These two cells are interconnected, and between these two points, I will draw one more resistance. This is the entire network, which is a simple network. And I am going to name every corner here. So this is represented as A, this point will be represented as B, this corner is represented as C, the next corner is represented as D, and this point will be represented as E, and again this is represented as F. Now our objective, still I am not discussing not stating the voltage. First we are trying to find out the nodes in this given network. It is the entire network. How many nodes are there in this network? Are you able to find out those nodes? How many nodes? Do you have any number in your mind? How many nodes are present? Only two nodes are present in this circuit or network, where one is at B. Three resistors are connected here. At this node B, three resistors, that means three components are connected. A is not a node because only two components, a cell and a resistor, they are connected. Here there is no other path is available. Okay, it is not a node. F, not a node. C, not a node. D, not a node. Node is the point where three or more than three components, resistors or cells, are interconnected. Again, E is also a node. Two cells and a resistors are connected. So therefore, it is again node. It will be represented by a dark spot. I hope you are able to see the dark spots. In order to analyze any circuit, first you have to note down the nodes. You have to mark the nodes. After that, we are going to begin. Now, since we are going to discuss the voltage rules, we need to know the values of all these cells. Sorry, I will take it as, instead of E, I will write it as F and this as G. E we need to represent for the cells. Okay, since there are two cells, the first cell will be having the EMF represented as E1. Okay, should I be writing its internal resistance? Sometimes yes, sometimes no. When it can be treated as negligible quantity and we can ignore the internal resistance. So here I want to write the internal resistance of the cell of EMF E1. I will represent it as an internal resistance R1, but I have not drawn the internal resistance. This internal resistance will be in series with the cell, and hence it will be in series with the resistor also. The first resistor, its resistance will be represented as R1. I will treat this as a second resistor. It will be having the resistance R2. Obviously, the third one will be having the resistance R3. Second cell will be having the EMF E2 and internal resistance R2. Again, R2 is in series with E2 and also R2. Only this circuit. R2 will be always in series with the cell. Internal resistance will be always in series with the cell. But it depends on whether it is in series with the R1. Depends on the circuit that you are on. It is not necessary, but it is. Now in this case it is in series. In order to avoid the confusion, I think I will not consider the internal resistance. Let it be only EMFs and external resistors. The circuit consisting this. R1 is negligible compared to these external resistors. Similarly, R is negligible compared to the external resistors. We ignore that. Okay, for our convenience only, to make the things simple. Now, second one is, how many loops are present here? First, we have identified the nodes. How many nodes? Only two nodes. Two nodes, which are B and F. B and F. Two nodes. How many loops? How many closed paths are available in the circuit? You can observe that. I will show you. Let us start from A, B, F, G, A. It is a closed path. It should end from where it starts. Therefore, the first loop that we have considered is A, B, then F, I will write here, then G, then back to A. This is one loop. Is there any more loops? Yes, other one. Second one, starting from B. Second loop. B, C, D, F, B. So I will write it as B, C, D, F, B. Is there any more loops? Yes, of course, there is one more loop. Third loop, which is starting from A, B, C, D, F, G, A. The larger loop. So there are three loops in the given circuit. A, B, C, D, F, G, D. Now we have identified the different. We are able to identify the loops and also nodes. Now I think we can discuss the Kirchhoff's voltage law. What does this suggest? Let us consider one of the loop. First, ABFGE. In this loop, there are three components. One is cell E1, other one is resistance R1, other one is resistance R. Only three components are there. It is very simple. Now we need to identify the currents. We have to put the currents in each loop. What are the different currents flowing in the circuit? This is our responsibility. We have to name the currents. Only this much will be given. Now we have to put the values of the current. First, the current which is flowing in this loop. That means in the branch G to A. Usually what we consider is that the current in the external circuit, when there is a cell, the current in the external circuit will be always from positive to negative. Therefore, the current between A and G, so that is represented as I1. Okay, it is directed away from the positive. Usually, that's the convention, so that's why I am giving the direction. I1 is directed away from the positive terminal of the E1. Then, what is the value of current between A and B? Again, same current, because there is no other path available. So, E1 and R1 they are connected in series. So, the same current I1 is flowing through the R1 also. Between G and F, no components, that means series, so for same current I1 itself. Okay. Now, when we consider this branch B to C, what is the value of the current? I will represent it as a I2. What should be the direction? Away from the positive of the E2. So therefore it will be like this. From B to C. Then again R2 is in series with the E2. Same current I2 must be flowing through the R2 also. Similarly here also. It is from same current, same direction should be retained. Therefore F to D. So this is the direction of the current line. We have represented two currents. One is I1, other one is I2. But what about the current flowing between the two nodes from B to F or F to B? What should be the direction of the current? It should not be the same as I1 and I2. It is different paths. So for the current should be represented as I3. Now my question is, what direction will you assign for the I2? Whether it is from B to F or F to B. Just use the common sense. These two currents, I1 and I2, are directed towards the B. That means they are flowing into the current. I3 cannot also in the same direction. At least one of them should be leaving. That's what the Kirchhoff's first rule, current rule suggests. Therefore, it purely depends on our instinct. It is not necessary that whatever direction that we have assigned should be correct. It might be wrong, but after analysis, whatever mistakes that we have done, it will be corrected. Now, so here, again, I3 is directed here, it is flowing into the other leaving the F, it is perfectly fine. Now we have assigned the direction. Now, we are going to apply the Kirchhoff voltage rule one by one to each of the loops that we have considered. The first, Kirchhoff statement of the Kirchhoff rule. It suggests that, or it states that, in a closed loop, algebraic sum of the voltages is equal to 0. Okay, algebraic sum of the voltages. Just like Kirchhoff's current rule suggests that algebraic sum of the current is 0 at a given node. Here, same type of definition. In a closed loop, algebraic sum of voltages. I will represent it as a small d. Algebraic sum of the voltages in a closed loop is equal to 0. That's the statement of the Kirchhoff voltage law. Mesh rule, junction, loop rule, same. Algebraic sum of the voltage in a closed loop is equal to 0. Okay. Now the question is, there may be two types of voltages. One is EMF, other one is electrons. When we consider the first two, there are three different types of the voltages. First one is EMF, E1. Other one is IR drop obtained from the Ohm's law, which is equal to I1 R1, one voltage drop. Other voltage drop is through the R3, which is equal to current into resistance. Current flowing in the resistance R3, therefore it will be equal to I3 into R3. According to the law, the algebraic sum of these three should be equal to how much? 0. I have not listed any symbol, which one is positive or which one is negative. I have not done anything. Now, how do you do that? I suggest, remember the Kirchhoff's voltage rule in the same form. Okay? Do not make any mistakes. There are two different ways. We can write all the EMFs on the one side and ion drops on the other side. But I suggest you to write everything on the one side only. One side of the equation on the other side should be 0. This can also be voltage which can also be stated like this: algebraic sum of the EMFs must be equal to algebraic sum of the ion drops. Same thing. But simple one is this one. Algebraic sum of the voltage is equal to 0. This one is algebraic sum of the EMF is equal to algebraic sum of the ion drops in a closed loop. Same law, stated in two different ways. But when we consider like this, then how to place the polarity? Which one is positive, which one is negative? How do you find out that? Now we have to consider the direction of traverse. In which direction we are traversing this loop? How we are moving? That is already decided. When we have written as A, B, F, G, A, then we have written how we are moving, not the current. How we are moving. That is from A to B to F to G, like this. That is in clockwise direction we are moving. It should be represented here, the clockwise direction. Now we are going to consider in the direction in which we are moving whether energy is increasing or decreasing. If energy is increasing, then we take it as positive. If energy is decreasing, then we take it as negative. Now, when we are deciding the polarity of the cell, we do not mean the current. But in deciding the polarity of the current, carefully observe. These rules are never asked in examination. But if you are not aware of these rules, then you will not be able to use the Kirchhoff's laws. So therefore, when we are traversing in the circuit across the cell, we are moving from G to A. Okay. That means when we are moving from G to A, we are moving from negative terminal, which is representing the lower potential, to the positive terminal, which is representing the higher potential. We are moving from lower energy to the higher energy. That means energy is increasing. It should be treated as positive. If energy increases, it will be treated as positive. Similarly, then we are moving from A to B. When we are traversing in a clockwise direction, we are moving from A to B. Then, what about the ion drops, ion number, whether it is positive or negative? Now we can assume that we know that current will always flow. When we consider the iron drop, we have to consider the direction of the current. For cell, it is not important. For iron drops, it is important, direction of the current. Current, that means the flow of the charges. It will be always from higher potential region to the lower potential region. If we assume that current is flowing from A to B, then A must be at higher potential. B must be at lower potential. That means since we are traveling from A to B in the direction of the current, what about the iron drops? In the direction of the current, potential is decreasing. So therefore, iron drop should be treated as negative. Okay. Then from B to F, again we are moving in the direction of the current itself. So therefore, iron drop should be negative. So therefore, E1 minus I1 R1 minus I3 R3 should be equal to 0. This is the equation obtained from the Kirchhoff's voltage law for the first mesh. Do you understand the concept? What if we are going to use this form? How do you write this? Same equation. But here we have changed the sides of the iron drops. We have written EMFs on the one side. It is written as it is. Even it is written like on the same side. But iron drops will be taken on the other side. So then what happens? Anything which is negative on one side, when it goes to the other side, it will become positive, and vice versa. Therefore, it will be equal to E1 should be equal to how much? I1 R1 plus I3 R1. This is how we can also write the equation for the Kirchhoff's voltage rule applied to a given loop. What does it suggest? If you are moving from negative to positive of the cell, it is taken as positive. If you are moving in the direction of the current, it is taken as positive. If IR drops and EMFs are written on different sides of the equal side, which one between these two you find simple? You have to decide which one do you find simple. Once you use that method, you should stick to that. Never try to confuse yourself. Don't try to use both the types. Either you can choose this way or the other way. I hope this is a lot easier. I will run the first one. It is little confusing. This one is easier, but writing the formula, the first one is easier. The second one is little lengthy. It suggests that algebraic sum of the EMF should be equal to the algebraic sum of the ions. Okay. Now, if you are moving from positive to negative, negative to positive of the cell, then E1 is treated as positive. If you are moving in the other direction, negative. In the direction of the current, iron drop treated as positive. In the direction opposite to that of the current, treated negative. Okay. I hope it is clear. Now, I will write the expression for the other loop. The first loop we have written as E1 is equal to I1 R1 plus I3 R. When we consider the second one, can you write the expression for the Kirchhoff voltage for BCD When we consider BCD again we are traveling in a clockwise direction. BCD clockwise direction. So for the second loop, can you write the expression? How many cells are there? Only one cell. How many iron drops are there? 2 iron drops across R2 and R3. Now, since we have decided the path, you can also reverse it. You can reverse the direction of traverse. But if you reverse the direction of traverse, instead of writing B, C, D, F, B, we have to write it as B, F, D, C, B. It depends on where you write the loop. You name the loop and write the loop. So it depends on it. But let it be clockwise. It can be anti-clockwise. But here it is treated as clockwise. Then what about the EMF? Is it positive? We are writing EMFs on one side, B2, and IR drops on the other side. I am not placing any sign convention, but I am just writing the IR drops. I2 current flowing through resistor, R2 current equal to I2 R2. Other one is again I3 R3. Okay. Now you have to place the sign convention. What are the sign convention? Write it here. I2 R2 I3 R3. I need a space to write another equation also. That's why I have rubbed it and rewritten that. So now, how to assign the signs? Since we are again moving from C to D, we are moving from higher potential to the lower potential. Okay. So therefore, energy is decreasing. E2 should be treated as negative. Since we are moving from B to C, we are moving in a direction opposite to the current. That's why I2 R2 I drop should be treated as negative. Again, we are moving from F to B in a direction opposite to current I3. We have to write I3 R3 as a negative. So therefore, minus E2 should be equal to minus I2 R2 minus I3 R3. If we reverse the direction of traverse itself, all these will become positive. Or mathematically, minus of A is equal to minus of B, then A is equal to B. Same. We will get the same result. It is not important that in which direction we are traversing, clockwise or anti-clockwise. Clockwise. We will get desired equation. You should know how to apply the sign convention. That is important. Now, let us consider the larger loop. Third, what should be the expression? Here, what are the EMFs? When we consider A, B, C, D, again in a clockwise direction. R3 is not involved in the loop. We are going from A, B, C, D, F, G, A. Both the cells are involved. So, I will write both the cells, EMFs of both the cells. E1, E2. Again, not place any sign convention. That is should be equal to. How many IR drops are involved? Only two IR drops. Which one? I1 R1, I2 R2. Okay. It is I1 R1, I2 R2. Two cells, two IR drops. What are the sign convention? Look at that. Since we are moving in a clockwise direction, like this, we are moving from, when we consider the cell E1, we are moving from lower potential, negative, to the higher potential, positive. We are moving like this. Energy is increasing. So therefore, E1 is treated as positive. Whereas, when we consider the E2, then we are moving from, since clockwise direction of traverse has been considered, we are moving from higher potential to the lower potential. Therefore, E2 is treated as negative. Okay. Then, iron rods. From A to B, we are moving in the direction of current I1. So therefore, I1 R1 is treated as positive. B to C, we are moving in a direction opposite to current I2. So therefore, I2 R2 will be represented as negative. I hope now you know how to write the Kirchhoff's voltage rule to different loops. Here we have obtained how many for this circuit? How many equations? 4 equations. You can see the 3 equations. Which one is the 4th equation? One obtained from the Kirchhoff's current law. When we apply to this node, Kirchhoff's node, 2 currents are entering the junctions. I1 plus I2, they are entering the junction. I3 is leaving the junction, so that should be equal to I3. That's the 4th equation. So therefore, when we are analyzing the given network, we need to find out all the possible equations. Actually, what happens is, we are given with the values of resistances. R1, R2, R3, they will be given. Their values will be given. EMF of the cells, they will be given. E1 and E2, they will be given. We need to find out the current flowing in each of the branch. That means, all we need to find is the values of I1, I2 and I3. That is, here in this circuit, there are only 3 unknowns. In order to find out the values of 3 unknowns, how many equations do we need? Minimum 3 equations. But we have 4 equations. Therefore, easily we can solve them. Everything else will be mathematics. If the values of resistance are given, substitute them here. EMFs, substitute them here. Then solve for the equation. You can find out the values. Mostly make use of this equation for the current one. So it will simplify more. Therefore, put the values, solve for this. Now, at the end, the one more important which can be asked for the examination. Either for the examination, you might be asked to write the definition of current rule and voltage rule, or their significance. I have already mentioned the significance of the Kirchhoff's current rule, which is conservation of charges. Similarly, what is the significance of the Kirchhoff voltage rule? Just look at the circuit or equations. It will be obvious. When you consider this equation, E1 is the EMF, which is supplying the energy. The energy supplied by the E1, it is used in overcoming the resistances to maintain the current in of resistances R1 and R2. So therefore, we can see that the amount of energy supplied is equal to the amount of energy used. Here also, this network, all the energy which has been obtained, so that will be used. The energy is not coming from anywhere else, or it is not going anywhere else. So therefore, here the total energy is conserved. Energy supplied from the cell is used by the components like resistors. It is not obtaining the energy from nowhere else, or it is creating the energy or destroying the energy. Therefore, the significance of the Kirchhoff's voltage rule is conservation of, are you able to see, energy? Can you see that? It is energy, last one. I think Y is not visible clearly. It is conservation of energy. So that is the Kirchhoff's significance of Kirchhoff voltage rule. So if possible, try to solve some problems, simple problems. Most of the cases, what happens is the Kirchhoff's rules will be more easier to find out the values of the current than the application of the Ohm's law. If you want to use the Ohm's law, so then you have to find out the effective resistance, then all the mathematics, it will become more tedious. You need to find out all the values, I1, I2. But if you use the Kirchhoff rule, we can find out the specific current only. If we want only I3, we can find only I3. But if you use the Ohm's law to find out the value of I3, you have to find out I1, I2 also. So therefore, this is most important. Practice it. When you practice it, then only you will be perfect. If you have any doubts, you can write in the comment section. Thank you. Thank you for joining.